Hello Abaqus user, welcome to Abaqus Acumen for quick and sound learning. Today's session we are going to handle how to do a contact convergence, and in the contact convergence we are going to work on how to handle rigid body motion between applicator and structured. So right now on my screen what you see is a typical hollow square pipe, and there is an applicator in the center which is applying around 100k Newton force. And today's purpose for this video is not to show you how to do a 3-point bend test, but this particular example is how to handle a rigid body motions in a contacting pair. And with this particular example we are going to use a star clearance option with a small sliding contact, and how this help to get a contact converge. So guys, I just exaggerated this problem a lot. So applicator and hollow square structure, there I put almost 20 millimeter gap, and this is not a tie connection. It is actually a small finite sliding contact between applicator and the structure. And you see, immediately I applied a load, it is immediately getting transferred. Even for with a huge gap of 20 millimeter, there is no rigid body motion or numerical singularity we are experiencing in this particular problem. And I just exaggerated this just to get you understanding how you can cleverly use a tool called a star clearance with a small sliding option contact, and you can solve a lot of contact issue without any convergence issue. So this is what we are going to solve it. The purpose is how to use a star clearance. Now quickly I'll go to the PowerPoint presentation so you'll get a more understanding what I'm talking. Rigid body motion in contact. Rigid body motion is not an issue for a dynamic analysis. You do an impact analysis where body is going to hitting. There is no issue for a dynamic analysis for the rigid body. But whenever you go in a static problem, rigid body motion occur when the body is not sufficiently restrained, and you start getting a lot of this message in a message file: numerical singularity warning, two regions are unconnected there, and large displacement indicated the unconstrained issue. And this is the typically when you have one body applicator or two connecting body, the contact has to take care of unconstrained motion. And if there is even a small gap, Abaqus or any other solver start throwing out error. There is two unconnected region, numerical singularity, high degree of DOF in particular unconstrained direction. And guys, this is very important, how we can solve this type of issue. Actually, most of the people do a mid-plane meshing and they keep it that gap, and whenever they apply force, and that cause a rigid body motion, and the reason for, and because of rigid body motion it give a divergence in a contact issue. So in numerical sense, in FE modeling wise, whatever you do it modeling, if there is a small gap or mid-plane, whatever you have done a meshing, that is because of this mathematical approximation or discretization, it is not necessarily there is a zero gap. So that create a lot of rigid body motion and unconvergence in a contact. Now how to handle this rigid body motion in a contact problem? So Abaqus as a solver, it has given a lot of tool how you can handle this rigid body motion in a Abaqus standard. There are something like a star contact control approach is there, star contact damping is there, but all with this approach or damping, there are some stuff in some damping energy is added, artificial energy is added, and that also driven your results. I'm not saying you should not use that, you should use it, but wherever possibly you can start avoid using damping option or star control option. The simple way which you can handle these or rigid body motion or put a zero gap between the two contacting body is using star clearance. And the star clearance is the option you can use with a contact pair, but there is a limitation. Star clearance you can only use with a small sliding option. For infinite sliding you cannot use a star clearance option. So guys, what we are going to do, we are going to do a very simple problem. We'll just we'll make a one hollow square pipe both end will put an end caster, will apply a 100k force on a in the middle section, will exaggerate it, will give a 20mm gap, will use a star clearance option, and will specify even though there are 20mm, mathematically there is a zero gap between this, and then we'll see how it's run. So guys, we'll start doing this problem. We'll create a part. I'll say shell 3D extrusion will do, deformable, it will be aluminum pipe, and it will be 3D deformable shell extrusion. So I'll quickly create 0, 0, 12.5, 12.5, minus 12.5, minus 12.5. So I'll get a two extreme corners. I'll just put it done. I'll just quickly put a dimension, just cross verify. Oh, it is 25. So I'll just extrude it, this shell, around 250. So shell is extruded by 250. I'll just split it in center. So I'll say I'll create a datum plane to split. So this is 250 and 125, there will be center line. So I'll create one plane at offset at 100, and I'll create one more at 150. So I created two plane. I'll just take a face and then select a datum plane to split it. I'll select another face, select datum plane to create it. So we quickly done that. I will quickly create a property. So it's a aluminum. We'll create elastic property. It will be 72 e power 0 MPa. So it's like a 73 GPa. And then we'll create a thickness 2.5 millimeter homogeneous shell. So we'll give 2.5. We've done that. Now we'll just we'll select all this region and we'll assign this. So we created, everything is done. Second part, will create applicator. So it's a discrete shell. We'll just extrude it. It should be 25 millimeter by 25 millimeter rigid surface. So again I'll create 0, 0 and then 12.5, 0, minus 12.5, 0. So it will be, guys, a straight line. We'll just create a straight line of 25 millimeter, and then you can just extrude this shell by 25 millimeter. So you get an applicator. Now we'll just create a assembly instant. So you take both, say apply, then we'll just quickly translate this. So we brought there. So we'll also translate this in z direction, positive z direction, 0, 0, 125. I should translate it by 100. So I'll just translate it 0, 0, 100. I'll just translate it another 12.5, so that will come in center. 0, 0, 12.5. So that comes in center. I'll also translate this quite high. This is just exaggerated it how you can use it. So 0 comma 20 comma 0. So now you see this is actually quite a bit high, and this is just to demonstrate how you can use a star clearance. It can be just a mid surface or little bit above for your convenience, and then you can use a star clearance. Now I'll just go to the property. I'll just first assign a reference point. We'll just assign for this. So this we are done. Now I will get to a mesh model. So let's first start with the aluminum pipe. Let's have a 2.5 millimeter as global. You can quickly mesh it, and then you go to applicator. Applicator is rigid and it will be master. So for applicator I'll put 3 and then mesh it. So you see there are two parts. We immediately mesh it. Both ends will be the end caster. There will this aluminum will be slave. This rigid applicator will be master. So first let's create a set. So node set end nodes. I'll just put this in some particular view, and then I'll just select it. I'll just put it properly. Yes, end nodes. So this is the end node 1, and then you'll create one more end node 2. Done. We'll also create a slave surface. So I'll go to the surface, create, it will be slave. Since it's a deformable body, so it will be slave, and the rigid body will be master. So I'll just select a surface. Done. Positive normal is on brown side, so I'll select positive brown. So the normals is up for this, and I'll also quickly create a master surface. Surface, I'll say master. I'll select this, and the positive brown purple is on upside, so I want a bottom side. So I'll select this brown, so it's a positive normal downside. So we selected the two surface. Quickly I'll create a frictional property. So you go to interaction property, you quickly create friction. We'll keep around 0.1. You'll define surface to surface contact. You select master, you select slave. Now this will be not finite sliding, it will be small sliding, because with finite sliding you doesn't get a star clearance option. So it will be small sliding. You select a clearance. So there are different options. Slave adjustment. Slave adjustment is one of the way to handle rigid body. We will get back to on that. So it will be clearance. You specify the uniform value 0, 0, and you say OK. So this is a contact defined. Even though there is a 20 millimeter gap, mathematically there is a clearance 0. So they are in touch with each other. Now I will create boundary conditions. So and 1, it will be end caster condition. So first we select that, then you can select end 2, so guys you can have both in one set also, there is no issue. And then we'll put one for applicator. For applicator it should be reference node other than y. So for applicator you select a displacement, not a symmetry, or it's not end caster, so that will be constrained in x, z and all rotation. Only it is free in y. So y constraint has to take care by contact. So we done that. We'll just quickly create a step. Create, I'll say contact convergence static. I'll put NL on. I'll put initial increment 0.01 or 0.01. You put that. I'll just put load, so it will be inside the step. Concentrated force, I'll just select that, done, and then it will be in minus y direction. So minus 100 k 1 2 3. So 100k load is applied on this. So I'll just save a file. Contact convergence, I'll just save a file. I'll create a job. We'll try to input file. I'll just show you how it looks like. So you'll get a better idea how this is star clearance is used. So I just open in text pad. We'll put star. So this is star clearance, master surface, left surface, and value 0. If you want to give physical value, they are part apart, you can give that value here also. So we'll quickly now put a data check and we'll submit a run. So we put for a data check. So just monitor. So let's wait actually if there is a preprocessor related error, or if there is some error related to solver. So it's a successful. So let's submit the run and just wait for results. So input file process completely, everything is, there is no issue. We can submit the run. We'll submit and just wait for results. So guys, results are out, and you can see now with star clearance and sliding contact how this is deforming. So the purpose was not to do a 3-point bend test, but to explore this tool called a star clearance. So I'll just quickly go back. So you can see their star clearance, master and the slave surface, and you are given value 0. And these two surfaces used in a normal sliding contact. So you see a contact pair interaction in small sliding surface to surface. So this type of tool you can use to get a contact convergence issue related to rigid body numerical singularity. And go ahead guys and use this in your day-to-day project. and explore more on the contact conversion side. Thanks a lot for watching this video. As all you know, this is a non-profit project, so we would require your support to take this project forward. So don't forget to like us and subscribe us. We need your support to take this project forward. We'll bring more videos on metal forming, rolling, a lot of different things. Thank you. Bye bye.